Hi guys, welcome back. Hope you had a great Thanksgiving. Figured I'd do one more video before I go to bed because I'm a little bit behind my quota. Sorry about that. We'll start with 10.98. It reads, a 10 milliliter sample of vinegar, HC2H3O2, requires 16.5 milliliters of a 0.500 molar NaOH solution to reach the endpoint in a titration. What is the molarity of the vinegar? Okay, so this is just like what we did in the last video, actually. We're going to start off with our milliliters. So it'll be 16.5 milliliters of NaOH. Then we're going to convert that into liters, because we have to do that for molarity, which, as we all know, molarity is liter, or moles over liters. Moles over liters. So we're going to have... Oh, God. I'm writing this way too big. My apologies. I'm going to shrink this down a little bit, so I actually have room to do the whole thing. So we have 16.5 milliliters. That looks really weird. Of NaOH. And we're going to convert that into liters. 1,000 milliliters on bottom. 1 liter on top. Then next up, it's going to be, we're going to use molarity to get into our other... we're going to use molarity to get into NaOH, so it's going to be 1 liter on bottom. And then the provided in the question says 0.500 moles of NaOH. Yes. NaOH. Next up, we use our moles to mole conversion, and this is what I was saying. This is how we get from NaOH to the vinegar. So, in our equation, it's a 1-to-1. Mole ratio. You can check the book. That should be provided for you. So it's 1-to-1. So it would be 1 mole of NaOH. Oh, I'm sorry. 1 mole of NaOH, and I'm going to convert that into vinegar, and it's 1 mole of vinegar. So that comes out to be 0.0825 moles of vinegar. And the goal of what we're doing, just like last problem, is to have it so we can do molarity, which is moles over liter. So now I've got our moles, so we're halfway done. Time to get the liters. And we're given in the problem, I believe it's 10 milliliters of vinegar. So we're going to convert that into liters. And this is the easy part. Liter equals 0.01. Yeah, 0.01. So 0.01 liters of vinegar. So now we're going to plug it into the molarity formula. So molarity equals 0.00825 moles of vinegar. And then we're going to have that over 0.01 liters of vinegar. And that comes out to be, when you do the math, it equals 0.825 molarity, or moles of vinegar. Boom. And that's your answer. There you go. 9.9 is an ABCD problem. It's going to be a lot harder. So I'm going to go really, really slowly and hope we all understand, because it took me a while to figure this one out too. It's actually really, really difficult. I wish you guys could have seen me rage when I would try to solve it and not be able to get it. It's ridiculous. I would absolutely freak out when I couldn't get it, because it took me 20 minutes of just sitting there just using calculator. But finally I got it. So here we go. A buffer is made by dissolving H3PO4 and NaH2PO4 in water. Part A asks to write an equation that shows how the buffer neutralizes added acid. Okay, so let me check my work here. So you have your H3PO4. Yeah, you got your H3PO4. And since we're adding an acid, the acid is what gives away. So on the right side, let me start up here. So the H2PO4 negative plus H3O, yeah, plus H3O plus. And that yields H3PO4, and that's where the H3PO4 comes in, plus H2O. So that's the equation that shows how it's done, and if you couldn't tell, the acid is the H. This is the acid because in the next thing it shrinks down and is what gives away the H. So in this H3 cancels and turns into an H2O, and then this H2PO4 gets the H and becomes neutral with its charge, and that goes down the charge. So that's how that works. Where's my washcloth? There it is. Now part B is asked to do the same thing but with a base, right? Yes. So this would be H3PO4 because we're going to switch sides now. H3PO4 plus OH negative, because that's the base I believe we're adding. Hold on. And then it turns into H2PO4 negative plus, sorry I'm in the way, I'll move 1 second, plus H2O. So in this equation, our base is this, and it gains a hydrogen. So we have this, we have our OH. Let's find our OH over here. There it is. It gained a hydrogen, so that's why it's a base, and that's how it neutralizes the acids, or whatever. You don't need to really understand the concept for this. Just make sure you can draw out the formula, and that's it. So now here's where it gets. Whew, this was bad. This is painful. I'm not gonna lie. So it says, calculate the pH of this buffer if it contains 0.1 moles of H3PO4 and 0.1 moles of H2PO4. The Ka for H2PO4 is 7.5 times 10 to the negative third. Alright, so we're given an equation. Okay, so that's the chemical equation we're given. And so basically we have to use our Ka to figure this out. So the pH is negative log. That's how so memorize that. No, negative log is basically how you get your pH when you're given something in scientific notation. I know that made 0 sense. Let me work it out. It'll make sense, hopefully. So let's plug in what we have for our Ka. We have Ka equals H3O plus and H2PO4, and that's over H3PO4. We don't include the water, the H2O, because that's liquid, and these are all aqueous, so that's why that's not going to be included. And since the K for all this equals 7.5 times 10 to the negative third. So I'm going to rewrite that in a more algebraically sensible way, because we're going to have to solve, we're going to get an x by itself, basically. So 7.5 times 10 to the negative third. So this is that. That's that. We need to solve to get H3O plus by, or H3O plus by itself. So what you do is you divide by H3O on both sides, and it'll all cancel out, and it equals, so pause, memorize this, I'm going to delete it to make room. And the new equation is going to be H3O plus equals, I'm going to plug in the number, so it's going to be equals 7.5 times 10 to the negative third. And that's going to be times the Ka, which came out to be, I believe it was 0.1 over 0.1. Yeah, 0.1 moles. They're both 0.1 in the problem. So if you don't know where these 0.1s came from, just read the problem, and I'll give what you need. This comes out to just be 1. So this times 1 is still 7.5 times 10 to the negative third. So we have our, whatever the heck you call that. Now it's time to get our pH. And we know the formula for pH equals negative log, and then the Ka for H3O plus. So we're going to have a pH equals minus log 7.5 times 10 to the negative third. And that comes out to be, sorry, it's like a gunshot or something outside, holy crap. 2.12, and that's your answer. So when you plug in your minus log, you get 2.12. So that's that. Now we're going to do letter D, where it gets slightly more complicated just because these numbers happen to be different and don't equal 1. So this is going to change through this process. So let's redo it. We have the exact same thing, actually. Everything should be exactly the same, except the numbers, the decimals should change. Let's check. Yeah. Okay, so literally, all the numbers are still exactly the same. We're doing the exact same thing. The only thing is these two numbers right here change. So this is part D. It tells us that we have 0.5 moles, or 0.50 moles of, what is it, where is it? 0.5 moles of H3PO4. And that's what was on top in our original Ka problem. So we're going to have 0.5 on top. And let me check, I think it was 0.20. Yeah, 0.2 moles of H2PO4 negative, yeah. So it's going to be 0.2 on the bottom. When we do the math for that, it comes out to be, let's see, 1.9 times 10 to the negative second. So that's how that works. And now we're going to do the exact same thing. So we have our H3O plus equals this. So I can draw one more equal sign and safely delete all of this stuff. Doesn't matter anymore, we've solved all that. So now it's time to do the negative log for this. So negative log, when you do minus log or negative log of 1.9 times 10 to the negative second, you get 1.72. And there's your answer. So thank you very much for watching this video. Happy Thanksgiving.